its advantages, features, we are going for the state model. So the state model is equally applicable for single input, single output and multiple input, multiple output system. And the state model is very simple because in the state model we are using the matrix algebra. So solving the problems by using matrix algebra is very simple, and the state space analysis is used in the digital computer because of their matrix notation. So in order to derive, these are the some of the advantages of the state space analysis. In order to derive the state equation for the series RLC network, the series RLC network is nothing but the electrical system. So in order to derive state model for any electrical system, we have to follow this procedure. The procedure is, first we have to select the variables. Here the variables are nothing but the voltage across the capacitor as well as the current through the inductor. Here the state variables for the electrical network are the voltage across the capacitor as well as the current through the inductor. And the number of state variables are nothing but the sum of L and C components in the given network. For example, in the given network, if you have 3 inductors and 2 capacitors, so you get 5 state variables. In the given network, if you have 2 inductors and 2 capacitors, then you will get 4 state variables. In the given network, if you have 3 capacitors, 2 inductors, then you will get 5 state variables. The state variables are nothing but the number of inductors and capacitors, the sum of inductors and capacitors in the given network. So after identifying the number of state variables in the given network, the number of state variables are nothing but voltage across the capacitor and current through the inductor. We have to write the independent KVL and KCL equations at the capacitor junction, and after that apply the KVL and KCL through the inductor. So whatever is applicable we have to apply. That means if you have the capacitor junction, you have to apply the KVL and KCL in order to solve the equation. So after applying the KVL and KCL, the resultant equation should consist of state variables, differential state variables and input and output variables. So let me explain this one with series RLC circuit. So here I am considering series RLC circuit. This is resistor R, inductor and the capacitor. So here in this circuit we are having one inductor and one capacitor. One inductor, one capacitor means the number of state variables here is, we are having 2 state variables. The state variables are nothing but sum of inductors and capacitor elements in the given network. So after identifying the number of state variables, if applicable, we have to apply the KVL and KCL in the given network. So here I am applying the KVL in this loop. So here the input source is Vi of t minus Vi of t, and I am assuming the current in this loop is I of t. Current in this loop is I of t. So minus Vi of t plus I of t into R plus L into di of t by dt, because voltage across the inductor formula is L into di of t by dt, plus voltage across the capacitor is Vc of t. Voltage across the capacitor is Vc of t. So minus Vi of t plus I of t into R plus L di of t by dt plus Vc of t. I am applying KVL in the input loop and I am writing those equation, that is minus Vi of t plus R into I of t plus L into di of t by dt plus Vc of t equal to 0. We know that for the electrical network, the state variables are voltage across the capacitor Vc and the current through the inductor IL. So we have to rearrange this equation in the form of Vc dash of t, that is Vc of t and IL of t, because these two indicates the state variables. That's why I am taking this di of t by dt, L di of t by dt in this left hand side, and I am taking this Vi of t, Ri of t and Vc of t into the right hand side. I am rearranging the equation in terms of Vc dash of t and IL dash of t, where Vc dash of t is nothing but d by dt of Vc and IL dash of t is nothing but d by dt of I of t or IL of t. So we have to rearrange the equation in this form. That's why I am taking minus Vi of t plus Ri of t plus Vc of t into the right hand side. So we are left with the equation L into di of t by dt equal to Vi of t plus Ri of t. This comes into right hand side, so minus Ri of t plus Vc of t will become minus Vc of t. So di of t by dt is also written as I dash of t. I dash of t. This I dash of t is called as the state variable. This I dash of t is called as the state variable. For electrical network, we have to write the state variable equation with the help of current through the inductor and the voltage across the capacitor. So here the I dash of t is also called as the state variable. So I am writing di of t by dt is denoted with I dash of t. So L into I dash of t equal to V into I of t minus R into I of t minus Vc of t. I am taking L into the right hand side, so it will become 1 by L Vi of t minus R by L I of t minus Vc of t by L. So I am considering this as equation 1. I am considering this as equation 1. I am considering this as equation 1. So up to now we are applying KVL in the input loop. We are applying KVL in the input loop and we are considering the equation. But here output side, the V naught of t is nothing but the voltage across the capacitor. The V naught of t is nothing but the voltage across the capacitor, that is Vc of t. So V naught of t is the voltage across the capacitor, and we know that the voltage across the capacitor formula is 1 by C integral of I of t into dt. 1 by C integral of I of t into dt, and current through the inductor is C into dV of t by dt. So output side we are having only one capacitor, so the voltage across the capacitor formula is this one. Now again apply derivation on both sides, apply derivative on both sides. So d by dt of Vc of t equal to 1 by C d by dt of integral of I of t dt. Integral and derivative term getting cancelled out. Integral and derivative term getting cancelled out here. So we are left with d by dt of Vc of t equal to I of t by C. D by dt of Vc of t equal to I of t by C. D by dt of Vc of t is also called as Vc dash of t. That is voltage across the capacitor. This is the state variable. This is the state variable. State variable. State variable. State variable. This is the Vc dash of t. Vc dash of t. So Vc dash of t equal to I of t by C. So this is the equation 2. This is the equation 2. Vc dash of t equal to I of t by C. We are rearranging the equation in the form of IL dash of t, that is current through the inductor, and Vc dash of t, that is voltage across the capacitor, because these are the state variables for the electrical network. The current through the inductor and voltage across the capacitor are considered as state variables for the electrical network. And with the help of equation 1 and equation 2. What is equation 1? Equation 1 is I dash of t equal to 1 by L Vi of t minus R by L I of t minus Vc of t by L. And equation 2 is Vc dash of t equal to I of t by C. So with the help of these two equations, I am writing IL dash of t equal to, I am rearranging those two equations in the form of matrix. So IL dash of t equal to minus R by L into IL of t minus R by L into IL of t minus VC by L into minus R by L into 1 by L into I of t, Vi of t minus R by L into I of t minus Vc of t by L minus Vc of t by L, that means minus Vc of t by L, this is 1 by L, and 1 by C into minus R by L into I of t minus 1 by L into Vc of t plus 1 by L into I of t. This is the first equation, and the second equation is Vc dash of t equal to 1 by C into I of t by C, I of t by C plus L into Vc of t plus 0 into Vc of t is 0 plus 0 into Vi of t is 0. So I am rearranging the equation 1 and equation 2 in the matrix form. This matrix indicates the state variable matrix. This will indicates the state transition. This will indicates the state matrix, and this is the input matrix. Similarly, at the output side, we are having the V naught of t, output voltage. The output voltage is nothing but voltage across the capacitor. So if I write the output equation, y of t equal to 0 into IL dash of t is 0 plus 1 into Vc of t equal to Vc of t. The output equation, y of t equal to voltage across the capacitor Vc of t. Just I am rearranging, I am applying the KVL in the input loop, and I am rearranging the equations in the form of I dash of t and Vc dash of t, and output side only we are having voltage across the capacitor, so that's why here we are getting the 1. Hope you will get some knowledge how to write the state space model for the electrical network. So thank you everyone.